Our solar system is not only home to planets and moons, but also to countless smaller rocks and dust particles called meteoroids. These solid particles orbit the Sun and can vary in size from large rocks as big as 1 meter to tiny dust particles. Most of the time, meteoroids fly around the Sun without trouble. But sometimes they end up on a collision course with a planet or moon. When they enter the Earth's atmosphere, their speed is extremely high, reaching at least 40,000 kilometers per hour. Luckily, Earth's atmosphere protects us. Meteoroids encounter friction from air molecules at 80 to 110 kilometers altitude, usually burning up completely and creating a trail of light that we observe as a shooting star or meteor. In very rare cases, a meteoroid may be large enough that part of it survives and falls to the ground as a meteorite. In short, a meteoroid is the object in space, a meteor is the light flash, and a meteorite is what remains on the ground. When a meteoroid enters our atmosphere, it also creates a trail of electrons that can reflect radio waves. This allows us to continuously observe meteors using radio antennas, even during the day or in cloudy conditions. Scientists from the Royal Belgian Institute for Space Aeronomy have installed a network called BRAMS, consisting of over 50 radio receiving stations in Belgium and neighbouring countries, and a dedicated emitter in Dorp sending a radio signal towards space. Reflected signals are usually brief, often fractions of a second, and are recorded by some stations. These signals, known as meteor echoes, provide valuable data for scientists to determine the meteor's trajectory, speed, and even size or mass. However, a challenge arises as radio waves are also reflected by aeroplanes, creating long-lasting signals that complicate the analysis of BRAMS data. BRAMS data is typically displayed as spectrograms. The horizontal axis represents 5 minutes, while the vertical axis represents the frequency of the recorded radio signal. Colors represent signal strength, with blue indicating a faint signal and red indicating a strong signal. The bright horizontal line in the middle represents the continuous signal emitted by the radio transmitter propagating near the ground. Meteor echoes typically appear as thin vertical lines. Larger meteoroids may occasionally produce more complex patterns, often during meteor showers. Inverse S-shaped signals are reflections on aeroplanes flying near the emitter. Why study meteors? First, meteors provide valuable information about the region of the atmosphere between 80 and 110 kilometers, which is poorly known. Scientists can also better understand the origin and spatial distribution of dust particles in the solar system. While Earth's atmosphere provides protection, objects in orbit, such as satellites and astronauts, are vulnerable to meteor impacts. With the increasing number of satellites, knowledge of meteor distribution is crucial. This is also true for future lunar and Martian missions.